Hello friends, my name is Amandeep Singh Bhui. I am an assistant professor in the Department of Mechanical Engineering, Amritsar College of Engineering and Technology, Amritsar. The topic on which I'm going to speak today is rotary air compressors. The contents that I'm going to cover in this topic are the classification of rotary compressors, difference between positive displacement and dynamic compressors, and the working and analysis of the roots blower. Now in the classification, we can see that the rotary air compressors, they are basically classified as positive displacement compressors and dynamic compressors. In the positive displacement compressors, we have three types, that is the roots blower, the vane type compressor, and the Lysholm or the screw type compressor. The dynamic compressors are of two types. One is the centrifugal compressor and the axial flow compressor. Now, the difference between the positive displacement compressors and the dynamic compressors is shown in this table. Now, in the positive displacement compressors, the atmospheric air is drawn into one or more of its compression chambers, which are then closed from the inlet. As the volume of each chamber decreases, the air is compressed internally until the pressure reaches the desired pressure ratio. Then the valve opens and the air is discharged into the outlet system. On the other hand, in the dynamic type of compressors, the atmospheric air is drawn into a moving set of blades where the air gains the kinetic energy. The air is then passed through the stationary blades called the diffusers, wherein the kinetic energy gets converted into the static pressure. Now, the first type of blower that we will discuss in this topic of today is the roots blower. Now, roots blower, it's a type of a positive displacement rotary compressor. It basically comprises of lobes, the rotary lobes, and the casing with inlet and outlet passage of air. The lobed rotors in an air-tight casing with the help of gears are installed in the external housing. The compressor inlet is open to the atmospheric air at one side and it is open to the delivery side at the other end. One of the rotors is connected to the drive, that is, the drive can be a motor, and the second rotor is gear driven from the first rotor itself. Now, the profile of the lobes is made cycloidal or involute in order to seal the inlet side from the delivery side. Here we can see the actual image, the cut section of a roots blower. In here you can see that one of the lobed compressors, it has a shaft protruding outside, and this shaft gets connected to the motor that drives this lobe, and at the back you can see there is a gear arrangement with which this is the driver shaft, and it drives the other shaft, the other lobe shaft also. Now here we will discuss about the working of the roots blower. The rotation of the rotors creates a space in the casing at the entry port as shown in the diagram. The air is drawn into the casing to fill the space. The flow of gas in the casing space continues till both rotors change their position. With the further movement of the lobed rotor, the air gets trapped in the rotor and the casing. As shown in the diagram, we'll be showing you the diagram in the next slide. The trapped volume of air is not internally compressed. It is only displaced at high speed from the suction side to the delivery side. Continued rotation of the rotor opens the discharge side of the rotor. Since the compressed air at high pressure is present at the delivery side, when the rotor uncovers the exit port, some pressurized air enters into the space between the rotors and the casing. This backflow of the flow of air is known as the backflow of air. This backflow of air continues until the pressure in the blower gets equalized. After the backflow, The air is compressed irreversibly at constant volume. Finally, at high pressure, the air is delivered from the blower to the receiver. In this slide, we can see the step-by-step working of the roots blower. In the diagram B, we can see that the air is getting trapped from the inlet side or the air inlet into between the lobes and the casing. And in this slide, in the diagram D, we can see the air trapped between the lobe and the casing here. And in diagram E, we can see that this air is now in contact with the discharge port where the high pressure air is available, and this high pressure air starts to move inwards towards the low pressure air that is trapped between the lobe and the casing is there. And this high pressure air movement takes place until the pressure of the air, the inlet air or the low pressure air is also increased, and then this air gets delivered at high pressure towards the discharge side. Here in this animation, we can see the actual working of the roots blower. The blue is the air. We can see that is the low pressure or the atmospheric air that is entering inside, and it gets trapped between the lobe and the casing, and then it gets the pressure of the air gets increased as it comes in contact with the high pressure air on the discharge side. Here in this slide, we can see there are two types of lobe roots blower compressors are there. Here we have a two lobe compressor, and in the diagram below we have a three lobe root blower. Depending upon the amount of air, mass of air required, we can increase the number of lobes, and that increases the mass flow rate of air. Now in this slide, we will do the analysis of the roots blower. The process of compression can be represented by a constant volume line, as the volume is not changing. So hence the pressure change from P1 or the atmospheric pressure to P2, the desired delivery pressure, is carried out at constant volume. So here in this diagram, in the PV diagram, we can see the pressure or the process taking place from state 1 to state 2, where the pressure rises from P1 to P2, and this change is irreversible, hence the line is a dotted line. Now considering let us suppose that the volume is V1 at the inlet, and the atmospheric pressure is P1 and the delivery pressure is say P2. So the work done for a flow process is given by minus integral of VdP, and if the volume is constant, so V can be taken out and from the integral, and so the equation becomes V1 into the final pressure minus the initial pressure. So this is the actual work done in the roots blower. Here if we consider an isentropic compression of air, so in that case the work expression is given by gamma upon gamma minus 1 into P1 V1, and in the brackets we have the P2 upon P1 to the power gamma minus 1 by gamma minus 1. So this is the isentropic work done, or the ideal work done is there. Now to calculate the efficiency of the roots blower, the efficiency of the roots blower is given by it's the ratio of the adiabatic work input divided by the actual work input. And here at the bottom we can see the formula here, and if we replace the pressure ratio P2 by P1 by RP is the pressure ratio, so the desired equation for the efficiency of the roots blower is given in the formula here. The efficiency of the roots blower decreases with the increase in pressure ratio. So from this formula we can see that if we increase the pressure ratio, the efficiency of the roots blower decreases. The compressor is suitable for a pressure range of 1 to 3.6. Thanks for watching this video.